Hello, we are Group 15, and for our project, we have decided to perform a safety analysis on the command and control system of the Boeing 737 MAX 8. We'll move into a short introduction of the project in this next section. The agenda is shown on this slide. We'll move through a background of the aircraft and mission, followed by a preliminary vehicle safety analysis and system selection. Following that will be a preliminary system safety analysis, and then the conclusion. For a project overview, we selected a 737 MAX 8 for this functional safety analysis project. The MAX 8 soared into the public eye after two fatal accidents, Lion Air Flight 610 and Ethiopian Airlines Flight 302. We will utilize the standard mission profile to determine required functions and perform safety and risk assessments on the aircraft. We want to perform an analysis of the maneuvering characteristics augmentation system, which was relevant to the Lion Air and Ethiopian Airlines accidents. In this section, we'll give the background on the aircraft and mission selection. The 737 MAX is a family of narrow-body aircraft manufactured by the Boeing Company. The development of this new series began in 2011, with the first flight of the 73 MAX achieved in 2016 and the first delivery in 2017 of a MAX 8. It was intended to compete with the Airbus A320neo line with reduced fuel use, improved efficiency, and lower maintenance costs. In order to achieve these goals, the MAX family featured a new engine that was larger and more efficient than its predecessors. The MAX 8 was certified in 2017, but however, after the two fatal crashes, the line was grounded by the FAA until 2019 and would not be recertified until 2020. The 737 MAX family technical specifications are shown here. In this project, we will take a closer look at the 737 MAX 8. The first hull loss of a 737 MAX 8 occurred on October 29, 2018. An incorrectly calibrated angle of attack sensor caused the Maneuvering Characteristics Augmentation System, or MCAS, to erroneously trim the horizontal stabilizer and causing the aircraft to repeatedly nose down. The flight crew did not have clear knowledge that the trim runaway checklist would disengage the MCAS, and so the system remained active and continuously placed the aircraft into an unsafe nose-down attitude until it impacted into the Java Sea. The Indonesian National Transportation Safety Committee listed the incorrect reactions of the flight crew as one of the contributing factors to the accident. The second hull loss occurred just under 5 months later on March 10, 2019, in a very similar situation involving MCAS. The left angle of attack sensor was damaged on takeoff, suspected to be caused by a bird strike, and again causing MCAS to command a nose-down pitch by trimming the horizontal stabilizer. In this case, the flight crew identified the runaway MCAS situation and disabled the trim, but their manual attempts to correctly trim were unsuccessful. In their attempts to return the trim to neutral, they reactivated the MCAS, which continued to make nose-down inputs until the aircraft crashed. The Ethiopian Civil Aviation Authority found the most probable cause was the repetitive nose-down inputs that caused significant dive rates near the ground.
For our group's mission profile, we use a 737 MAX 8 traveling from Los Angeles to Atlanta on a medium-haul flight. The distance traveled for this flight is 1,940 miles with an average flight time of 7.5 hours. The cruise altitude of the MAX is 41,000 feet, but this trip will be at 33,000 feet, where the air is more stable and less turbulent weather appears. The cruise speed for this flight is 530 miles per hour. The cargo capacity for a MAX 737 is 7,275 pounds, and the fuel used on this flight will be about 20,000 pounds, or a little under half of the 45,000 pound fuel capacity for a 737 MAX. For this commercial flight from Los Angeles to Atlanta, the mission profile will include a primary mission with steps of taxi, takeoff, climb, cruise, descent, and landing, and enough fuel for a reserve mission that will also include a climb, cruise, descent, and landing. The 737 MAX on this flight will fly in Class A airspace, which is between 18,000 and 60,000 feet. Coordination at all steps with air traffic control will be performed during primary and reserve mission steps. A mission phase-based functional diagram for a commercial Boeing 737-8 MAX flight include 4 aircraft functions of loading and unloading cargo on the ground, controlling the aircraft in the air and on the ground, and decelerating the aircraft while on the ground. These operating functions for each aircraft function are listed below and are typical for a commercial flight.
Now that you have a basic understanding of the research background and our mission objective, we would like to take you through the safety analysis exercise. This section introduces our preliminary vehicle safety analysis. Our approach aligns with Aerospace Industry Standard ARP 4761 Alpha, which starts by defining aircraft level functions, mapping their interactions, and identifying critical hazards, which then allows us to develop our system fault trees, identify assurance levels, and perform probabilistic risk assessments. You are looking at the block definition diagram. It is the functional breakdown of the key systems of 737 MAX 8 and their core functions. The key systems consist of propulsion, command and control, hydraulics, environmental control, etc., each necessary for safety-critical operations across different flight phases. To your right is the activity diagram of the 737 MAX 8 functional interface. It synthesizes how the key systems interact. It becomes quite useful when we're analyzing how faults propagate through the systems and deriving the probabilistic models.
Our Vehicle Function Hazard Assessment, FHA, kicks off with the functions of propulsion and environmental control and assesses hazards such as engine failures and loss of cabin pressurization, and further breaks down the effects and the severity and likelihood of the hazards based on each specific phase of flight. The FHA continues with the functions of power management, aerodynamics, and command and control with hazards such as loss of hydraulics, control surface hardovers, and air data failures. The FHA concludes with the functions of structure, navigation, and communication, with failure conditions such as landing gear collapse or failed extension, navigation failure, and radio failure. The vehicle risk assessment combines the hazards and their severities and likelihoods developed in the FHA, aligned with the risk matrix for commercial aviation in FAA Order 8040.4c. Notably, there is a slight tendency for hazards during the takeoff and landing phase to be more severe due to the criticality and reduced aircraft performance in those phases of flight. The exception is 5.3, loss of air data sensor, which corresponds to the command and control function during a climb, assessed as catastrophic and remote. The target levels of safety are shown here for the 737 MAX 8 for the vehicle hazards at each phase of flight. The targets are shown as a goal to be less than the designated probability value. The probability values for the corresponding likelihood definitions were taken from ARP 4754 and FAA Order 8040.4c.
Now that we have a better understanding of vehicle safety matrix, we're going to deep dive into Vehicle Functional Fault Tree Analysis, FTA. We begin fault tree analysis with the propulsion system. This diagram shows dual engine failure caused by independent faults or common failure event, such as fuel starvation. We assign probabilities using FAA guidelines and operational data. This diagram shows single engine failure caused by independent faults, either loss of fuel supply, faulty engine, or stalled compressor can lead to a catastrophic event. Loss of cabin pressure is a hazardous condition. This fault tree highlights possible causes such as ECS failure, outflow valve issue, and fuselage breach. Each contributing event is assigned a probability and linked through logical gates. This diagram depicts the hydraulic loss scenarios. The failure events consist of pump failure, fluid leaks, and power loss to hydraulic controllers. Even though the system has redundancy, simultaneous failures can result in loss of control surfaces. Control surface hardover is a catastrophic failure. It can be induced by actuator failure, runway input, or MCAS logic misfire. Fault probabilities were sourced from incident data and aligned with known component failure thresholds. In this diagram, we analyzed the loss of air data sensor. AOA sensor failure and feedback inconsistencies can trigger MCAS malfunction. We modeled this using both hardware and software failure contributors. We are closing the vehicle fault train analysis with navigation failure. Navigation failure affects pilot situational awareness. It can be caused by errors such as GPS and INS, which cascaded from sensor loss, electrical faults, or interference.
From here, we moved into our system selection. We selected the command and control system, and we'll provide a short overview. The command and control system has the primary responsibility for controlling the aircraft in flight. Typically, the system is driven by the flight crew in the cockpit through physical controls, such as a yoke or a stick. In modern fly-by-wire aircraft, instead of the pilots having direct control over the aircraft's control surfaces, their inputs are fed through a series of avionics designed to allow for more precise and stable control, as well as automation. The system often has control laws relying on additional input from feedback sensors to assist pilots through specific flight phases. Like the rest of the aircraft, this system is heavily integrated and relies on the successful functions of other systems, such as the propulsion system, to provide the necessary amount of thrust for a specific flight condition. It would be expected that the system would be able to function through a number of redundancies to safely continue operation of the aircraft, with potential catastrophic failure resulting in a loss of control of the vehicle.
MCAS was introduced to 737 MAX to enhance pitch stability in a certain flight condition. Unfortunately, the system relied on an input from a single angle of attack sensor, making it prone to enormous activation. The single point failure led to tragic Lion Air and Ethiopian Airlines crashes, where the MCAS repeatedly forced the aircraft nose down despite the pilot input. This slide shows the physical architecture of the 737 MAX MCAS system. A critical issue here was the reliance on a single angle of attack input with the limited cross-checking between the FCC. This configuration made the system vulnerable to sensor failure without proper redundancy. The logical architecture on here. Logically, the MCAS system had several shortcomings. Before the accident, the system lacked angle of attack sensor redundancy and did not properly handle sensor disagreement. MCAS would activated based on a single potential fault input. Post-update changes including angle of attack, input cross-checking, and the MCAS activation limits, and a better pilot feedback. These updates improved tolerance, pilot awareness, and significantly reducing the risk of repeated failures.
Now we move into the preliminary system safety analysis, or PSSA.
This is a structured analysis that evaluates how well the safety requirements are implemented in a system architecture. For 737 MAX, we focused on MCAS, or Maneuvering Characteristic Augmentation System, due to its role in recent accident. Our objective here was to evaluate the MCAS within the border command and control system to identify the design gap, the safety critical function, and the potential failure points. The expected outcome is through understanding of MCAS vulnerability, which will inform strategies.
The FHA at the system level evaluates each function's failure impact on aircraft safety. We utilized ARP 4761 alpha criteria for severity and likelihood assignments, linking each condition back to mission phases and safety objectives. This slide continues the FHA, finalizing severity likelihood mapping. This forms the basis for risk prioritization and leads to our development assurance level assignments. Based on the FHA results, we assigned FDALs to each function. Catastrophic level failures like propulsion loss are assigned FDAL-A, requiring the most stringent verification and validation. We further decomposed system-level FDALs to individual hardware and software items. The item FDALs trace to functional needs, supporting aircraft safety integration and certification readiness.
This fault tree analysis is for a runaway trim control just like the 737 MAX accidents, which is why this fault condition was selected. With the revised MCAS system, now 2 AOA sensors instead of 1 feed into the MCAS system. Additionally, trim surface command limits are implemented to prevent a horizontal stabilizer deflection that would cause an unrecoverable nose-down pitchover. Finally, the redesigned system only permits 1 MCAS activation per sense highway event, meaning the only way for repeated activations of MCAS is if the AOA signal were to repeatedly oscillate above and below that threshold implemented in the control law for the highway event. This fault tree analysis is for an AOA disagree that is not enunciated to the aircrew and deals with the sensor suite and feedback and alerting system functions. This fault condition was selected because the 737 MAX aircraft fleet prior to the accidents did not show an AOA disagree alert on their flight display unless the airline selected that option, which was a contributing factor to the accidents. With the revised MCAS system, it is standard now that in that scenario an AOA disagree message will show on the primary flight display. In this fault tree, for an AOA or airspeed/altitude mismatch to not be alerted to the crew, not only must there be some type of failure or mismatch between the probes or pedostatics, but also some type of flight control hardware or software failures for the alert to not display, as well as not be enunciated by the voice warning system.
This is a common cause analysis, and this is where identifies the failures that can simultaneously affect multiple systems. For the 737 MAX, the shared cause was the angle of attack sensor failure, which affected both the MCAS and the flight display. Post the accident, modification focused on improving logics, and this risks by implementing sensor across validation. This is the PRA matrix and post-accident update. The PRA matrix visualizes the severity and the likelihood of a different failure mode. Pre-accident, the MCAS-related failure fell into very hazardous or even catastrophic zone. Post-accident updated moved this risk into a safer region by improving sensor redundancy, pilot alert, and control authority. These updates were coordinated with FAA recertification and requirements. This slide categorized the failure mode across the flight envelope. The takeaway here is that situational awareness and trim authority are most critical during these high-risk phases. So on this slide, the MCAS PRA analysis outline failure consequence of activation. The key issue was the single point angle of attack failure that led to repeated nose down trim input. The risk management recommendation included implementing angle of attack redundancy, enhancing pilot authority, and more robust software oversight. On here we analyzed risk from sensor suite itself, particularly the angle of attack. The lack of sensor cross-checking meant that single faulty sensor could mislead the system. On here we have a feedback and alert system. Before the update, the alert like the angle of attack disagree indicators were either absent or delayed. Post-accident changing this alert and improved pilot training. This measure increases the pilot situational awareness and response time in abnormal condition.
Now we move on to the Common Mode Analysis, or CMA. In this CMA, we'll be looking at the command and control system for a 737 MAX 8 aircraft. This is a qualitative analysis as listed in ARP 4754, using engineering experience to support independence of systems or a vehicle. In this case, we will select two command and control functions seen on a 737 MAX aircraft. These are a sensor suite and the feedback and alerting system. In this part of the CMA, we look at the sensor suite, which helps monitor the aircraft's angle of attack, speed trim system, and MCAS system. Common cause mode listed on the left include cruise speed controls, flight angle of attack controls, landing speed controls and brakes, and the pilot mechanical controls. Corresponding common cause failures and independency review and comments are also listed. Since the focus of this analysis is around the MCAS system after the Lion Air and Ethiopian airline accidents, as you can see on the flight angle of attack controls line, the AOA sensors have been duplicated, and the information being relayed back to the pilots help adjust the MCAS system, which improves safety post-accidents. In this part of the CMA, we focus on the feedback and alerting system, which is a system of controls that monitors the aircraft operating variables and alerts crew members, passengers, and pilots when necessary. For the common cause modes in this case, we look at the master caution warning system, the angle of attack alarms, and the takeoff configuration warning system. Again, common cause failures and independency review and comments are listed in the corresponding rows. Since the focus is on MCAS, we look at the angle of attack alarms and see in the independency review and comments that the angle of attack sensors have been duplicated, the software has been updated, and this now relays correct AOA information back to the pilots to adjust MCAS, improving safety post-accidents.
We have performed a number of analyses for the 737 MAX 8 over the course of this project through our preliminary vehicle and system safety analyses. Our three analyses concluded the adjustments made to the 737 MAX MCAS following the two accidents significantly improved its redundancy and overall efficiency. The command and control system had been extremely vulnerable with a single point failure, combined with a lack of informative training for flight crew on how to respond. With improvements to the number of redundant information sources for MCAS and improved control laws, pilots would be able to retain control of the vehicle in the event of an unintentional MCAS activation. This project allowed us to implement several types of safety and risk assessments against a real-world commercial airliner and provided understanding for the significant amount of development and testing required for complex modern systems. Additional recommendations for this project include continuing to explore other potential failure modes on the 737 MAX for other systems. This could also include broadening the scope of these assessments into other flight phases and other systems, and potentially drawing comparisons to other modern airliners with a similar level of complexity in their aircraft systems. Vehicle improvements could include continuing analyses into the MAX failure modes and implementation into aircraft software, with continued vehicle testing to discover interactions and edge cases between systems. These improvements continue as the testing and certification phase is in work for the 737 MAX family.